Okay, welcome everybody. So now we've proven that for a vector space V, any basis has to contain exactly n elements. It's unique. I can't have one basis that has 3 elements in it and another basis for the same vector space that has 4 elements in it. So now we can define the dimension of a vector space. So if V is a vector space spanned by a finite set of vectors, then we say V is finite dimensional, and the dimension of V, which we write as dim V, is the number of vectors in the basis for V. So let's take a look at some special cases. So if we have a vector space V that consists of just one vector, the 0 vector, then we would say that this vector space has dimension 0 because we do not need any vectors to span this set. So that's kind of a special case. If we have a vector space that just consists of the 0 vector, it is dimension 0. Not every vector space is spanned by a finite set. So it's possible that you encounter a vector space V which is infinite dimensional. And we'll give an example of one such infinite dimensional vector space below. So to review these terms, we looked at the vector space P2, which is the vector space of all polynomials of at most degree 2. And this has dimension 3. It has a basis, for example, that consists of elements 1 and t squared. So we could say that P2, since it has dimension 3, it is isomorphic to R3. We have a map from P2 that is 1-to-1 and onto R3. The next example is we've taken a look at the vector space of 2x2 matrices, and that vector space has a basis that consists of 4 vectors. So this vector space has dimension 4, and therefore it is isomorphic to R4. And for an infinite dimensional vector space, one example could be the vector space of polynomials of any degree. So we're not setting an upper limit on the degree, and this is infinite dimensional. If we wanted to construct a basis for this, we could try 1 and t squared and t cubed, but we would have to keep going forever. So this is infinite dimensional vector space. Okay, so let's take a look at an example where we can look at the dimension of the subspace of a vector space. So far we've defined the dimension of a vector space as the number of vectors in a basis, and we've shown that that number is unique. So that's what we call the dimension of a vector space. For subspaces, we define the dimension the same way. The dimension of a subspace H is going to be the number of vectors that we need in a set in order to form a basis. So here we've got a subset H, which is a subset of R3, right? This is consisting of some column vectors in R3. And so to form a basis, we need a set of vectors that is going to span this subspace. So we'll first identify these vectors. So we can see here that any vector in H we can write as a scalar A times 3, 6, 2, plus some scalar B times -1, 0, 1. And by taking linear combinations of these two vectors, we're going to be able to get any generic vector in set H. So here we've identified one vector v1 and a second vector v2. So our basis seemingly is going to look like 3, 6, 2, comma, -1, 0, 1. This is a spanning set, and now we also just want to make sure we could have one vector as a scalar multiple of the other, in which case it would violate the linear independence property that a basis must have. But we can see here clearly these two vectors are linearly independent from each other. This one has a 6 in its second position. This one has a 0. So there's no way I could take some multiple of this vector and wind up with this vector over here. So here's a basis for this subspace. it consists of two vectors. So therefore, we would say that the dimension of subspace H is equal to 2. And notice it is less than the dimension of the entire vector space R3. So that's a good thing. We would not really expect to pick a subset of R3 and find out that it has a dimension which is larger than the vector space itself. And let's take a look at the picture in R3 of this subspace. So here's R3. It's the space spanned by x1, x2, and x3. And here is this set that we just identified in R3. So here is this vector v2, which is 3, 6, 2. And here is this vector v1, which is minus 1, 0, and 1. I just called them different vectors, but when we look at the span of these two vectors, v1 and v2, they span a plane in R3, and notice it's a plane that goes through the origin. So any subspace of R3 has to contain the 0 vector, which in this case is the origin. So this subspace H is actually just the plane spanned by vectors v1 and v2. And so to wrap up this part of the video, let's consider what all possible subspaces of R3 could possibly look like. So if I have a subspace H sub 0 that consists of just the 0 vector, so that would be the vector 0, 0, 0 in R3, which graphically we think of as the origin, this would be the only subspace of R3 that has 0 dimension. So there's only one 0-dimensional subspace, and that's the subspace that contains just the origin. We could have 1-dimensional subspaces, and these would be represented by a set whose basis consists of just one vector. And the span of that one vector would be a line in R3 that again must contain the 0 vector. So it's going to be a line through the origin in R3. So here's a picture of a 0-dimensional vector space, which is just the dot at the origin. And any 1-dimensional vector space in R3 would look like a line in R3 that passes through the origin. For dimension 2 subspaces, like the one we just looked at on the previous slide, these would be any subspace that has 2 basis elements. So if we look at the span of 2 linearly independent vectors in R3, that forms a plane in R3 that's going to contain the 0 vector. So any 2-dimensional subspace of R3 is going to be some plane that sits in R3 and contains the origin. And lastly, 3-dimensional subspaces of R3, well, there's only one 3-dimensional subspace of R3, and that's the entirety of R3 itself. So these would be the sets of all subspaces that have a basis that consists of 3 linearly independent vectors that span all of H2. Though we can set up different bases for R3, any basis that we set up that has 3 linearly independent elements, well, that's going to span all of R3.